Everyone knows if you shake up a carbonated drink, it explodes. But why is this? Well, here I have an identical bottle with a pressure gauge fitted to it, and I want you to make a prediction right here. If I shake up this bottle, will the pressure increase, decrease, or remain the same? And while you're thinking about that, let me tell you this video is sponsored by Squarespace, the all-in-one platform for building your online presence. More about Squarespace at the end of the show. Okay, I hope you've made your prediction and registered it in the poll up here. This bottle has been sitting stationary for a few days at room temperature. You can see the pressure reading is about 3 atmospheres, 330 kilopascals. And I'm going to shake it up and see what happens. Ready? In 3, 2, 1. And the pressure is still the same. You might suspect that, well, maybe this bottle is all out of gas. Maybe it wouldn't explode on me, so just to make sure. Yep, it would go. So it's not an increase in pressure that causes a bottle to explode like that. So why is it? Well, you shouldn't feel bad if you predicted that the pressure would increase, because in fact that explanation was published in New Scientist in 1986, leading many other scientists to come forward saying that is not the real explanation. So we will find out what it is after we explore the second perplexing physics problem. Consider this. If you put identical ice cubes in a cup of fresh water and a cup of salt water, which ice cube will melt first? Again, you can register your prediction by answering the poll here. Now, as you're thinking about that, I want to show you the setup. Okay, so here I have regular fresh water. Just going to fill up each cup. Then I'm going to add about a tablespoon of salt into this cup on the right. Now, if you know a bit about chemistry, you may recognize that adding sodium chloride to water actually takes energy, and so it lowers the temperature of this solution by a little bit. So I've got a thermometer just to check, and I'm going to let this solution sit here for a while so that it comes back up to room temperature. Okay, have you made your prediction? Let's put these ice cubes in 3, 2, 1, and they're off. Watching ice cubes melt. Isn't this entertaining YouTube? It has only been about a minute, but already I can tell that the ice cube in the fresh water is melting faster than the ice cube in the salt water. How does that make any sense? I mean, we put salt on the roads to melt ice faster. So why isn't this ice cube melting as fast as the one in fresh water? Well, that is what I'm going to explain. But first, let's go to the third perplexing physics problem. Okay, here I have a metal ring and a closed loop of chain. And I'm going to do this all in one take so you know that I'm not playing any tricks. So what I'm going to do is dangle the chain and then hold the ring over it, like so, and then I'm going to drop the ring. And exactly what you expect happens. The ring just falls off this chain, and of course, how could anything else possibly happen? Because, well, it's a closed loop of chain and a closed ring. But if you think about it really hard, you can get the ring to stick on the chain. Have a look at that. So how does this work? Well, I think we're going to have to go to some slow-mo footage to really see what's going on. Now, I'll let you in on the secret. When you want the ring to stick on the chain, the key is to let it go on one side before the other side. So I'm going to let it go with my thumb first, and it'll just sort of slide off my finger. And by doing that, the ring will stick on the chain. It introduces just a little bit of rotation so that the ring rotates about 90 degrees and slides down the chain like this. As it does, these pieces slide up the sides. And when you get to the bottom, it's almost like this piece at the bottom gets sucked into the middle of the ring, and then at the last minute gets pulled around, and it snaps on, and it's locked on like that. So that's how you can get a ring locked onto a closed loop of chain. So back to problem number 2. Why is the ice cube in fresh water melting faster than the one in salt water? Well, I think we can get a better view of this if I add a little bit of food coloring right on top of the ice cube. Because the water coming off that ice cube is cold, it's more dense than the surrounding fresh water, and so it descends in the glass, and that brings more warm fresh water up to meet the ice cube, melting it faster. Whereas on the other hand, in the salt water, as the ice cube melts, that fresh water is actually less dense than the salt water around it. And so it stays, that cold water that just melted off the ice cube stays around the ice cube, in effect insulating it from the warmer salt water around it.
Okay, that seems like a very plausible explanation and maybe a convincing demonstration, but in the edit, me from the future, I decided that, maybe this wasn't the best way to explain this because, well, you're just dropping food coloring in there, and maybe food coloring would just float on the surface of salt water anyway and sink in fresh water, so not a good demonstration. So a better demonstration, I thought, might be if we used colored ice cubes to begin with. Okay, I know there's a lot of food coloring in there and that makes things kind of hard to see, but I think you can clearly see the currents of cold water streaming down to the bottom of the cup in the freshwater side and not in the saltwater side. So I think this does clearly show what I was saying.
The cool water that comes off the ice cube doesn't go down deep into the cup. Over here you can see that's what's happened. So why do shaken carbonated drinks explode? Well, first let's explain why the pressure doesn't increase in the headspace when you shake it up. This is because of equilibrium. When you pick up a bottle of soda in the grocery store, it's been sitting there for a few days. So the dissolved gas, the dissolved CO2 in the liquid, is at equilibrium with the gas up here in the headspace. And that equilibrium only depends on the temperature and the pressure of gas in the headspace. So no amount of shaking is going to change the pressure up here. For most soda bottles these days, that pressure is about 3 atmospheres. Now, you can actually hear those 3 atmospheres of pressure get released when I open the bottle. But of course that's not messy because it's just gas coming out the top. There's no liquid. But now the liquid is no longer in equilibrium. I mean, it used to be under 3 atmospheres of pressure and now it's just under 1 atmosphere, ambient pressure. And so because of that, there is more dissolved CO2 in this liquid than would be at equilibrium at this pressure. And so the CO2 starts to come out of solution and, well, those are the bubbles that you taste. That's why this drink is fizzy.
Non-equilibrium beverage.
And if you leave it open, those bubbles will keep coming out until the whole drink goes flat. Now I'm going to put the pressure gauge on top of this bottle so we can actually see the CO2 coming out of solution and increasing the pressure right here. And if I left this bottle alone for long enough, the pressure would eventually come back to equilibrium, 3 atmospheres. But as you can see, it is a very slow process. And that's because it's actually quite hard for dissolved gas like CO2 to spontaneously come out of solution. One way that I can accelerate this process is by introducing nucleation sites into the liquid. And one example of a nucleation site is a tiny gas bubble. So if I shake up the bottle, what I'm actually doing is introducing little nucleation sites, tiny air bubbles, into the liquid, and that makes it easier for the CO2 to come out of solution, and so we'll see this pressure increase much more rapidly. You ready? I'm going to shake it up in 3, 2, 1. And there you see the pressure has quite quickly come back to about 3 atmospheres, 320 kilopascals. So if you shake up a closed carbonated drink that's been at equilibrium, well, you are not increasing the pressure in the bottle, but you are introducing tiny air bubbles into the liquid, which act as nucleation sites. Some of them cling to the walls of the bottle. So when you go to open it, those bubbles do 2 things. First, they expand due to the decrease in pressure, and that pushes up the liquid above them. And second, they act as nucleation sites, allowing the dissolved CO2 to come out of solution much more rapidly, and so that's what leads to the carbonated drink explosion. But this suggests a way to disarm a shaken carbonated beverage, and that is by flicking the walls of the bottle. That gets rid of those bubbles that are clinging to the sides and allows you to open the bottle without incident. Ha! It worked. Now, is there a way to introduce nucleation sites into a carbonated drink without shaking it? Yes, that's exactly what you're doing when you put a Mentos in a carbonated drink. The rough surface of the Mentos acts as a nucleation site, which allows the CO2 to come out of solution much faster, creating the soda fountain.
Me again. So when I showed this video to Diana, the physics girl, she asked whether paper straws have more nucleation sites than plastic ones. And to be honest, I'm not sure about the research around this, but there are some other YouTube videos showing how drinks overflow when you put a paper straw in, and also my little preliminary analysis with this paper straw show that it does indeed create more bubbles than a plastic straw. So if you needed another reason to hate paper straws, well, there you go. They make your carbonated drink more fizzy as it comes up the straw.
This has been 3 perplexing physics problems. If you have any other perplexing science problems, put them in the comments below. Hey, this portion of the video is sponsored by Squarespace, the all-in-one platform for building a professional website, online store, or portfolio. In fact, about a year ago, I remade my website, veritasium.com, on Squarespace, and I found it so much quicker, easier, and cheaper than going through a web developer who I always had to contact in order to make changes. Squarespace gives me great analytics, so I can see who's coming to the site and when, from where, and what they're spending the most time on. And that allows me to see what people are really enjoying, which helps me decide what to make next. Now, if you're just getting started, well, you can purchase your domain directly through Squarespace, which saves you the hassle of setting up domain name servers and all that kind of stuff. Plus, each domain comes with free Whois privacy, because nobody wants a domain that reveals all your details. And if you want to run email campaigns, Squarespace can do that, making the look and feel of all your communications consistent. Or how about an online store? Squarespace can do that too, with e-commerce templates, inventory management, streamlined checkout, and secure payments. So it really is the all-in-one online platform, and you get 24/7 email support. Anytime, day or night, you can reach a Squarespace employee in their offices where they will respond to your query, typically in about an hour. So what are you waiting for? Check out squarespace.com for a free trial, and when you're ready to launch, use code Veritasium to save 10% off your first website or domain purchase. So I want to say thanks to Squarespace for sponsoring this video, and I want to thank you for watching.